Okay, so what is the game plan, guys? What are we doing? So, the game plan is we will be starting on enzymes. So, enzymes. Enzymes is tricky. Enzymes is going to take us a full 2 weeks to properly get through. So what's going to happen with our shoot workshop tomorrow is, because with the workbook, how I've kind of done it is merged the two sets of questions, so for week 6 and week 7 together to just give like a bigger enzymes module. But what I plan to do in the shoot workshop tomorrow is go through your first assignment, give you your second assignment, and sort of talk a little bit about how assessment's going to obviously be changing moving forward with 1014 BPS. Again, look, same rules, guys, same deal. If there's any technical issues on my end, please let me know. I'm trying to sort of monitor and keep an eye on everything. My microphone's been playing up a little bit today, so just let me know if I sort of start sounding a little bit like a robot. And of course, post questions, okay? Let me know what's happening, guys. Let me know if you want me to speed up or slow down or anything like that. Okay, so enzymes. Let us get started. What is the game plan for enzymes? So basically, we're just going to start off by sort of looking at the general sort of 5 classes of enzymes and sort of very, very quickly look at some of the general descriptions of them. So like how they basically work. The reason why I want to be quite brief with this is simply because a lot of the stuff there in terms of your like how the reactions occur, you will do that in Chem 1B a whole lot. So I'm not going to talk too much about that. We're going to talk about the basic chemical process of how an enzyme works and why it is enzymes are so good, why it is enzymes are so useful. Whoops, there we go. And we're going to be looking at some catalytic pathways. We're going to be looking at a good key example here is chymotrypsin. Okay, we're going to be looking at the mechanism of action of how chymotrypsin works. And just generally try to understand the basics of enzymes as a whole. Then what we'll do next week is sort of look more so at the math of enzymes and looking at how we can calculate various things. Does that make sense, guys? We're all happy? We're all good with that? Go. Okay. So, where am I going to put me? I might go down here. Here we go. So, what is an enzyme? Okay, in essence, guys, an enzyme is a protein in which its goal... I thought I had a different slide here. Never mind. In which it is essentially a protein in which its overall goal is to bind to a reactant and turn it into a product quickly. Now, just be aware, guys, with chemistry, we refer to them as reactants and products. So again, how I remember it or how I think of it is that reactants react to produce a product. However, with enzymes, we obviously don't have, or we don't call them reactants, we call them substrates. So what we see here is that we have our reactants going to our products. However, with enzymes, how they primarily function is that they will take our substrate and convert it into a product a lot quicker. And we're going to be explaining sort of the basis on how that works today. And just a couple of things, like we'll be going through this in a little bit more detail, but how I want you to just be aware of these couple of stages is that we have our molecule A, and our goal, what we want to do, is to turn molecule A into molecule B. Hi Brock, I'm unable to join you on Zoom. Zoom's tomorrow. We'll be doing the Zoom tomorrow. So Zoom's for Tute Workshop. We hit up the YouTubes for our lecture. So yeah, our goal here is to turn molecule A into molecule B. And the first step that's going to happen here is that it needs to make contact with our enzyme. It's pretty much impossible for our enzyme to perform the work unless our substrate, in this case molecule A, actually physically touches it, physically binds to it. And what this will do is it will form an enzyme substrate complex. What does that mean? Enzyme obviously is our enzyme. Our substrate is our substrate, and a complex is simply more than one thing. So an enzyme substrate complex is simply describing an enzyme and a substrate that are in physical contact. Then catalysis happens. What does that mean? Magic and witchcraft and all sorts of weird and wonderful things happen here. And then suddenly, bippity boppity boo, we now have an enzyme product complex. What this means is that the enzyme and the product, so the chemical reaction has finished, but that product is still bound, it's still attached to that enzyme. And then what's going to happen is it's going to dissociate, it's going to leave. And that's our final step, and that's what we're looking at down here. When do we have our tutorial tomorrow? It's at the usual timetabled. Oh, sorry. Oh, no, that was my bad. I said your workshop is tomorrow. I'm getting myself muddled up with my anatomy class. I'm very, very sorry. We will have Zoom later on today. Oh, it's all going to the pits already. I'm very sorry. That is my fault. So what we'll do is when we finish off our lecture, I will stop the YouTube recording here, and then I will fire up Zoom. So I will let you guys know when we're going to kick off there. First the door, now the tute. I know, man. It's a mess here. It's an absolute mess. Oh dear me. Cool beans. Yeah. My apologies again. That one's on me. That one's on me for that one. Okay, so let's have. I'm not gonna dwell on the whole history of the enzyme and how it was discovered, but basically some old mad lads here. What they did was they had maybe 4 eyebrows between them, and what they essentially found was they were able to purify urease, and what that did was it essentially broke down or hydrolyzed our urea, which we can see down here, and split it up into 2 lots of NH3 and CO2, carbon dioxide. Now, why this is powerful? I mean, urea will automatically do this. Urea will automatically decompose to create, ammonia and carbon dioxide. That's not a big deal. What is a big deal is the speed, how quickly it is able to do it. So urease enhances the rate of urea hydrolysis at a pH 8 and 20 degrees Celsius. Okay, so these are quite standard conditions. They're not too buck wild. By a factor of 10 to the 14. That is buck wild. This part is ridiculous. So just to again put this in perspective a little bit, if a given quantity of urease completely hydrolyzes a given quantity of urea. So if we just had a pot of urea. I said a pot, a container, a set quantity. Oh man, of urea. And we add urease to it, and basically it takes 5 minutes to become completely hydrolyzed. How long would that take if we were to just leave it outside? If we would just leave it, say, on my desk here, how long would that take? The answer, 950 million years. That's huge, yeah? 5 minutes versus 950 million years. That is the potency. That is the how effective enzymes are in terms of accelerating or speeding up a chemical reaction. Now, again, I'm not going to go too thoroughly into this, but these are a lot of some of the clinical applications of enzymes. So where we actually see them in use. So enzymes are also incredibly important for diagnostic measures. So when, say, someone has had a heart attack, sorry, there we go. What's going to happen here is that we can actually do a blood test and we can actually measure this enzyme called troponin. And what this enzyme is, it's critical for ensuring cardiac muscular contraction. So if there has been a heart attack and there is evidence, or we're trying to find evidence of, damage or cell death, what we're going to be doing is we are searching the blood serum for troponin, because if we find this here, what that tells us is that, okay, cardiac tissue has been affected, cardiac tissue has died, so this person has probably suffered a heart attack. Another example here is looking at some metabolic disease due to enzymes deficiencies. So instead of us looking for the presence of an enzyme, we can also look and say, hey, is this enzyme doing what it's supposed to do? Is it functioning as intended? So an example here is looking at Wilson's disease. So if you are deficient in P-type ATPase, which is a cation transporting enzyme, again, not going to go too much into that, what essentially happens is that the body can't really transport or move copper as effectively as what it needs to. And what can then happen is that you get a buildup, you get an overabundance of copper, and it can cause oxidative stress and cause damage to your liver. We also can use enzymes in the lab. So we can use ELISAs. These are enzyme-linked immunosorbent assays. And what this does is that we use antibodies that can bind to or attach to an enzyme. And what it will do is it will detect the presence of a substance. So if we want to look at how much of a particular, say, type of antigen is here, or how much of a receptor is here, we can essentially bind it, and then react it with an enzyme, and we can use that to then measure the overall amount of our product. Enzyme inhibitors. So again, we have enzymes damn near everywhere in our body. So what happens if they're not doing quite what we want them to? So a good example here is SSRIs. So these are selective serotonin reuptake inhibitors. So for those of you who are a little bit rusty, serotonin that's your happy feel-good hormone. So serotonin, that's like the birds are chirping, the sun is shining, and you just feel good. You just feel happy. So in cases of depression, what can happen is that the body is just not getting enough serotonin. So what the body will do is that it will release serotonin, it will bind in that synapse, trigger an effect, and then we have these enzymes that will scoop up and get rid of that serotonin from the synapse. So what we can do as a type of medication is that we can actually inhibit that enzyme that is scooping up and trying to get rid of that serotonin reuptake. And that means that more serotonin will exist in that synapse for a longer period of time. This one we will be talking about a lot more. Ooh, not this week. No, we'll be talking about it when we talk about sugars, when we talk about carbohydrate, and that is looking at how we can measure blood glucose in diabetes, and also looking at enzymes as therapeutic agents. So this is sort of just a little bit of an explanation, a little bit of background here as to some of the clinical and biochemical applications of enzymes. But of course, the most important, the most productive, the most succulent and delicious type of enzyme use is, of course, fermentation. Yeah, we use it in beer, in wine, in spirits, in all sorts of things. These lovely yeast will chew up sugar and will poop out ethanol, to which we harness and isolate, and we use to sterilize various things. Okay, let us now talk about some of the advantages, because being able to catalyze a reaction or being able to speed up a reaction is not the same thing as an enzyme. So, for instance, with a chemical reaction, we can speed it up by, changing things like maybe the pressure of the system or changing the temperature, these sorts of things. And this is very, very common, doing a chemical reaction and you take your beaker or your test tube or whatever and you put it in a water bath or you put it on a Bunsen burner or something like that. You heat it up, you increase that temperature. However, yes, that is all well and good. That will speed up the rate of a reaction. We can also add, we have acids that can catalyze reactions and this sort of thing. However, enzymes are a different kettle of fish, and they are there are far greater advantages for enzymes. And the first one, and a very important one, is greater reaction specificity. So if we look at this enzyme down here at chorusmate mutase, what this will do is that this substrate could turn into... this isn't chorusmate mutase, that's the enzyme, but our substrate here could turn into one of 4 products. And, aside from just doing the reaction and looking at percent yields or maybe looking at overall reaction stability between our 4 products over here, that could determine which way the reaction will go, but we have no way of controlling that unless we use an enzyme. Enzymes are good as well because it can control what type of product is formed. So it's very, very good for avoiding side products, and it's very, very good for that reaction specificity. The next one is milder reaction conditions. I don't know about you guys, but I really do not feel like having to go and, sit on a Bunsen burner every morning and basically set myself on fire to make sure my body is doing its regular chemical reactions needed to survive. Yeah, I wouldn't recommend it. So we can have milder reaction conditions. We don't need to have a pH of 2 or a pH of 3. We don't need to have temperatures of 60, 70, 80 degrees. We have conditions that are, conducive to, life. Higher reaction rates. Typically, they're faster as well, just to put, salt in the wound. And, of course, capacity for regulation. You can't go to, say, hydrochloric acid or sodium hydroxide or sulfuric acid, something like that, and go, hey, I know you've got a tough day, but can you, not be an acid just for a little bit? Hydrochloric acid, I know it's in the name, but just for 10 minutes, can you just try not being an acid for me? No, it's. I mean, you can try asking very nicely. It's not going to work though. What we can do, however, is chemically we can regulate these enzymes. We can turn them on and we can turn them off. Does that make sense, everyone? Are we all good so far? We're following along. Oh dear. Okay. Okay, so I just want to give here just a bit of an example of what I mean by substrate selectivity or substrate specificity. So here we have phenylalanine, okay, one of our lovely amino acids. So if we are wanting to react this with an enzyme called phenylalanine hydroxylase, okay, so what it's going to do is it's basically going to take phenylalanine, it's going to slap a hydroxyl group on there, and it's going to turn it into tyrosine. So again, if we have in our body, we have a lot of phenylalanine, but we need to create more tyrosine, this is something that we could do. So if we look at this reaction, we've got L-phenylalanine, cool. The reaction, it'll bind to our enzyme, phenylalanine hydroxylase, and we will get tyrosine. Cool, job done, awesome, everything worked as intended. Now, what happens if we got D-phenylalanine? It's literally the same molecule, but instead of L, it's D, so it's that enantiomer. It won't even bind. It won't even bind to the enzyme, okay? It's not going to fit. Now, if we take this structure, which is sort of similar, it kind of looks close to, if you kind of like squint your eyes and blur your eyes a little bit, it's similar to L-phenylalanine. What this is saying is that it will bind. Now, to be clear, when I'm saying binding, what I'm meaning is this part. Like the substrate will bind to the enzyme. Cool. That's what I'm referring to here. So it will bind, but nothing will happen. There won't be a reaction. So what will more than likely happen is it will bind, but then just leave again. Does that make sense, everyone? So again, that just goes to show like the degree of enzyme specificity that I was referring to. Okay, next one, enzyme classification. Okay, looking at some of our enzyme classes. So basically these main classes are just provide a brief summary into how that enzyme works as a very general holistic view. Let's do this one. Also, too, just to keep note, most enzymes will end in A's, okay? It will have that suffix ASE. Oh, Google, don't do that. And what that means is, so like, you know, isomerase, ligase, most, like a lot of enzymes do follow this rule. However, there are a few exceptions, which we'll talk about a little bit later on. So this is just a cool little image just that outlines what is happening here. So like isomerases, what we see here is that it will catalyze or convert a substrate to a different isomer. So it could go like, say, cis and trans. So it will contain the same atoms and only the bonding pattern or arrangement will change. Let me come back to here. Transferases. What's going to happen here is that essentially it's going to catalyze the transfer of two different things, so it's going to swap them around. Hydrolase, okay, this uses water to hydrolyze, so hydro meaning water, and lase basically to split. Or basically it's short for lysis, so lysis meaning to split, to break apart. So liases, okay, this is again enzyme, but instead of using water to cleave them apart, it's just able to catalyze the cleavage of, say, carbon-oxygen, carbon-carbon bonds to split them apart as a byproduct. So pyruvate going to acetaldehyde, we can see that splitting that off and releasing CO2 as a byproduct. Isomerases, okay, again, just turns around and makes it an isomer. I've already explained that one. Oh, I missed this one. Oxidoreductase. Sorry, these ones are in a different order. Oxidoreductase uses redox in order to catalyze these reactions. We can see that by, you know, if we look at NAD plus going to NADH. Okay, what would I expect you guys to know over these two slides here? Let me do this. Here we go. What I would expect you to know across these two slides is essentially the names of these enzyme classes and very briefly, like a very generalized understanding as to how they work. So oxidoreductase, it catalyzes a reaction by using redox. Okay, hydrolases, it splits or hydrolyzes a substance. Uses water to split them apart. That sort of thing. Okay, what we're going to talk about now are some proteolytic enzymes. Proteolytic enzymes are, of course, involved a lot in the GIT, okay, our gastrointestinal tract, to help us break down proteins that we may eat. These are secreted by the pancreas. It is also secreted by the stomach as well, depending on the enzyme, of course. And what it does is that it will act like a big pair of chemical scissors and will chop them up. So what we were doing in week 2, we were looking at the formation of a peptide bond. What it will do is actually the opposite. Okay, it'll use water and it will split them apart, and that's what we are essentially seeing here. So we can see our peptide bond, we can see water here, water can come in and split them apart, giving our carbonyl group and our amino group. Is everyone following me so far? Please let me know if I am going too fast, or if I've lost any of you guys or anything like that. Okay. Naturally, I've got to try and include some kind of SpongeBob if I'm, talking about biochem in any way. So, one enzyme I do want to talk about briefly is Romulan. So Romulan is an enzyme. It basically will work in breaking down and hydrolyzing some of these proteins. It's very common for a lot of people to use this as a meat tenderizer, okay? And why is this good? Because it's very good at breaking down and cutting up collagen. So remember, we were talking about collagen, the alpha helix, alpha chain, all that kind of jazz. Romulan is a very effective enzyme by using water to essentially cleave and break them apart. So it's good for sort of tenderizing and breaking down that meat. This is also commonly found in pineapples. This is why if you eat a lot of pineapple, aside from it being acidic, it will also make your mouth sort of tingly and will also start to sting after a little bit, because you thought that you were eating and digesting the pineapple, but actually it's kind of eating and digesting you at the same time. So yeah, that's kind of what is happening there when you are when you eat too much pineapple. Excuse me. Now, proteolytic enzymes and specificity. I'm going to talk about this a little bit more right at the very end of class today. But essentially, to again come back to what we were talking about with enzymes, looking at that specificity. What happens if you don't eat enough pineapple? You miss out on that sweet pineapple goodness. That is what happens. So what's happening here with specificity is that enzymes are incredibly specific, and there's no exception when we're looking at these proteolytic enzymes. And what we see is that these proteolytic enzymes will cut up our proteins in different spots, depending on what type of bond is there and the shape of and the composition of the protein. So for instance, an enzyme we're going to be looking at the end of today, chymotrypsin, cleaves after an aromatic residue. So if we've got one of those aromatic amino acids, it will go after there and it will cut. But again, we're going to talk about that a little bit more in a moment. So this is just to sort of keep in mind that with our proteolytic enzymes, they are still very, very specific in how they are cut and how they are cleaved. Okay, what I'm sort of explaining here too is that, just because they are incredibly specific in terms of how they cut and how they cleave, they sometimes will go, okay, that's close enough, which is kind of an awful example. But what we can actually do is with some of these proteases, they can occasionally go to and cleave an ester, because the peptide bond is very similar in terms of, if we just look at it here, we've got our carbonyl group. With our peptide, we've got a carbonyl group. But instead of binding to this amine, it's binding to this oxygen here. So it is very, very similar. And in some cases, the proteolytic enzyme will still cleave this ester to form our acid and alcohol. This can be useful for us within the lab, basically to allow us to measure experimentally, say that the presence of a particular acid, or looking at the presence of this alcohol, we can measure that and determine the efficacy of this particular enzyme and stuff like that. It gives us a metric in which to measure. So what have we done so far? We've looked at very, very broadly the catalytic power of a biological catalyst, and we've kind of very briefly compared it to a regular catalyst. But what I want to sort of go through and what I want to sort of cover now is the how and the why. So, of course, by doing this involves our free energy. Sorry, just let me change this a little bit. Sorry. There we go. That's a bit better. Sorry. Now, with our enzymes and looking at free energy change. So, when we're looking at the molecules of a living cell, they possess energy due to these vibrations, due to the rotations in these chemical bonds, and therefore the energy is stored in there. So, when we're looking at this free energy, it's measuring the energy of a molecule which, could be used to, in essence, perform work. And we looked at this when we looked at protein folding. And we looked at how by changing that free energy, it means we are able to maintain that negative delta G, so that the folding of that protein would be spontaneous. Now, looking at two different enzymatic reactions here. So in the same way with our protein folding, how we can detect whether it is spontaneous or non-spontaneous, we can do the same thing but with enzymatic reactions. So if we have an exergonic reaction, let me do this. If I have an exergonic reaction, what this is going to do is it's going to be releasing energy outside, so it's going to be giving us a negative delta G. So this is important because this essentially means that it can occur spontaneously. It is able to do it by itself. It does not need an additional source of energy, or it doesn't need to change the favorability of a reaction. However, shoe on the other foot, we also have endogonic reactions. And what this does is it requires energy or input from the surrounding system in order to allow this reaction to occur. So this is a positive delta G. So this is energetically unfavorable for the system. Now, does that mean that these endogonic reactions just don't exist? No, of course they do, but they're just not energetically favorable. So what do I expect you guys to know from this? I would expect you to just know that, an exergonic reaction is a negative delta G, and an endogonic reaction is a positive delta G. Now, looking at our changes in free energy as the reaction occurs, what we have here is, say, A plus B reacts to form C plus D. So if we look at this free energy change, if we're looking at the change before, looking at our free energy before the reaction occurs, okay, the energy of our reactants, we can see our two curves here. One is with an enzyme, one is without an enzyme. One up here, this is the energy of our reactants. They are both the same. Now, the reaction occurs, many wonderful, so much chemistry, all of it, all of chemistry happens here. And what happens then was that we have our enzyme and we have our product. But look at the energy. Yeah, the energy of our reactants and the energy of our products. There is no change. Okay, the change is only with these curves here, which I'm going to talk about a little bit later. Now, delta G is useful for us because it measures and relates to equilibrium. Okay. So if the change in our delta G is 0, what that means is that our reaction is in equilibrium, and it means it's not moving one way or the other way. Oh, sorry, I should reword that. It's moving both ways, but at an equal rate. I'm going to come back to this. Here we go. This is what I want to talk about. So, free energy is loosely looking at and loosely describing here we go. How much energy can be utilized in this chemical reaction? Okay, so therefore we look at this change in delta G. Now, enzymes don't change the delta G. Enzymes don't change the delta G, okay? They don't do it. Okay? We need to keep that in mind. Enzymes do not alter the delta G of a reaction. Okay, the delta G of a reaction tells us how much of this free energy is being utilized, and it refers to the change in our chemical reaction. That's what I'm going to explain more down here. So, if we start to compare these things now, if we're looking at the change in our delta G of a reaction. So here we have an exergonic reaction, and here we have an endergonic reaction. So with our endergonic reaction, we are going from reactants, and then it requires a heap of energy, and then here are our products. So energy has to be added to this because the overall amount of energy in our products is higher than what it is in our reactants. Whereas if we look at our exergonic reaction, we have our reactants here. We have this big spike in energy, and then boom, after we pass this point, because this point here was the amount of energy our reactants had. So once we move past that point, energy is being released from this reaction and out into the system. So it is releasing energy. So what we then have, I want to talk about this yet. Okay, the only thing I really want to touch base on here is looking at delta G and delta G naught. All delta G naught is looking at is essentially the change in this free energy. So like what I'm seeing here, this free energy between our reactants and our products, looking at that change but under a standard condition. So what that means is that all of our substrates are at 1 molar concentration and at a pH of 7, and it's sort of standardized conditions. So what we can then do is by looking at our delta G and looking at the change in a delta G, what this tells us is the favorability of a reaction. Let me do this. Here we go. So what this means is a spontaneous reaction. So what we were looking at over here, this spontaneous reaction, this doesn't tell us anything about speed. All this tells us is the favorability of a reaction and telling us essentially whether this reaction will go ahead spontaneously. That's all it tells us. So, for instance, if we look at this chemical reaction here, combustion of glucose in oxygen. So if we take glucose here and we react it with oxygen, it's going to form carbon dioxide and water. This reaction is really favorable, super duper duper favorable. Okay, we can see that by this negative 686 kilocalorie per mole. So it's highly favorable, but it doesn't tell us anything about speed. Okay, this can still take a very long time unless we do have an enzyme or some kind of catalyst here to speed up this rate of a reaction. In this case, by sort of lighting the fuse and setting it on fire. Okay. Is everyone following me so far here? Everyone's all good? Yep, awesome. Awesome. I'm not used to you guys being so quiet. Okay, so that's what we were looking at here in terms of our rate of reaction, because the free energy change and the equilibrium constant are closely linked, because it all comes down to our equilibrium and how our reaction will proceed forward. So if we have a look at this reverse reaction here, we've got A plus B is reacting together to form C and D. So this is a reversible reaction, and we are in equilibrium when the amount of A plus B reacting forward is the same as C and D reacting backwards. So why is this important? And again, you guys would have learnt this in, I believe, Chem 1A, if I'm correct. And if you didn't do it in Chem 1A, oops, I forgot to put myself back up. And if you didn't do it in sort of Chem 1A, I'm sure you will definitely do it in Chem 1B. Okay, this equilibrium. Now, if we have a look here at, the change in our equilibrium constants, which again, it comes down to our fractions. So if we have a large equilibrium constant, okay, if we have a larger number on our top versus the bottom, what that tells us is that the reaction is going to mainly favor the products. If we have an equilibrium constant that is less than 1, or quite a low number like here, this tells us that it's going to be a higher number up here. This is going to be mainly our reactants or our substrate being formed. And of course, if the equilibrium constant is equal to 1, then that means that we are at equilibrium. The amount of products and the amount of substrate are equal, so there is going to be no net movement. Now, just to clarify, this large negative change in our free energy, this reflects a favorable reaction to equilibrium. What this means is that the reaction will sort of want to proceed forward to our product. This has nothing to do with speed. We haven't covered speed yet. So we can have a reaction. Will we be tested on Gibbs free energy, or just need to know it exists? In terms of the math of it, will I ask you to do any math calculations on Gibbs's free energy? No. No, I won't. But I do expect you to know the difference between a positive and a negative delta G, and I expect you to understand, what that information is sort of telling you. Same thing as with protein folding. I'm not going to get you to do calculations to do with, Gibbs's free energy. But I do expect you to know and understand what information it's telling you. So what we are looking at here is that even if we have a large negative delta G, this is indicating a favorable reaction, meaning that it wants to, the substrate or our reactants want to make our product. This has nothing to do about the rate of the reaction itself. We can still have a highly favorable spontaneous reaction that will occur slowly. Now, what I'm showing you here is just to prove a point, I guess. So for instance, if we have a low KEQ, okay, if we have a low equilibrium constant, what this is telling us is that the reactants are highly favored. Okay, so again, product over substrate. So if we have a very low number, this means our substrate is going to be a higher number than our product, which means that our substrates are going to be favored. The reaction is not wanting to push forward to our products. It's wanting to favor the reactants. And if we compare the equilibrium constant here to our delta G, what we are seeing here is that these are very positive values. The less favorable our equilibrium constant is towards the product, so as we are moving further up, the number is getting smaller and smaller, meaning that the reaction is more and more favoring the reactants or the substrates. What we are seeing here is that same change is reflected with the delta G. As the equilibrium constant is getting lower and lower and lower, as it's favoring the reactants more and more and more, we are seeing this delta G get more and more positive. Now, shoe on the other foot, if we look down over here, the equilibrium constant is getting higher and higher. And this is also reflected in our delta G. We are getting more and more negative because this reaction is more and more favoring the product, which means it's getting a more negative delta G because it's more favorable. Does that make sense, everyone? Is everyone all good there? Okay, I want this one. So, this is just a quick little summary slide that I've put together for you guys, just as a bit of a recap. So, the change in the free energy, all it does is it's giving us information as to whether the reaction can proceed forward with or without an energy source, or without any energy input. So if we have a negative delta G, what this is going to tell us is that we have an exergonic reaction and that it is spontaneous and it will not require an input of energy. Whereas if we have an endergonic reaction, it will not occur spontaneously. It will not occur by itself. So the second thing here is that the equilibrium constant, it's directly proportional to this delta G value, because again, what they're telling us is very similar things here. The equilibrium constant, is it going to favor the product or is it going to favor the reactant? What we are looking at here with our delta G in our endergonic or exergonic reaction is it going to proceed forward spontaneously or not? The third point here, the delta G of a reaction depends only on the free energy difference between the reactants and the products and is independent of how the reaction occurs. Now, that was an interesting point. Let me talk about that. What that means here is just looking at this graph here, okay? The change in the energy of our reactants and our products, it doesn't matter what's happening here. It doesn't matter what's happening with our chemical reaction itself. We're going to talk about that more in a moment and what is happening here with respect to enzymes. But what's important to keep in mind is that this change of reactants and this change with products, we can't change that. We cannot change this. We cannot change this. Where we do have the ability to change things is here. But again, we're getting a little bit ahead of ourselves. We'll talk about that a little bit more in a moment. And the last one, okay, the delta G of a reaction provides no information about the rate, okay? All it's saying is that let's say I am on the Gold Coast, okay? I am in the Gold Coast and I want to travel to Sydney, okay? This, right now, my home, Gold Coast, is my starting point. Sydney is my end point. That is where I wish to go. How long will it take me to get there? No idea. Why? Well, it depends. If I take a plane, 2 hours. If I take a car, 10 or 12 hours. If I walk, a million years, knowing me. But you see what I mean? This delta G and this equilibrium constant, it's essentially telling us which direction our reaction will want to move. It doesn't tell us anything about the speed in which we get there. Good luck, yeah. Okay, so guys, what we'll do now, let's have a quick 2 second, let's have a quick 5-minute breather, okay? Stand up, stretch your legs, top up your coffee, okay? Do what you need to do, and we shall push on with enzymes in a moment. Alrighty, crew, welcome back. How are we going with it so far? How are we feeling? How are we going? Whoopsies. How are we going with it all so far? Is it all making sense, guys, or is it just sort of just a lot of information to take in? Okay. Right. Okay. So, all G, I love it. So let's come back to where we were. So we'd spent a lot of time looking at this free energy change, and we're looking at this change in equilibrium, and sort of what that means, like what these two factors, how they link together. Now, as you know, spoiler alert, it's kind of in the title, but what is happening here with enzymes? I've spent a lot of time talking about these, rate of reactions and all this sort of stuff, but I kind of haven't spoken about enzymes yet. So enzymes, what they do is it will accelerate the reaction rate. Okay, so the same equilibrium point is reached, and that's important. Okay, now it's like how I explained to you guys, like me wanting to travel, say, to Sydney, just as an example. Maybe not right now, but who knows, maybe in the future. That was a very unfortunate time to need to cough. It's not like I want to go to Sydney, so I want to get there faster, so I'm going to take Sydney and move it closer to me. No, that's not how we can do this. However, I can use an enzyme to get me to Sydney quicker. Okay? So enzymes are proteins that work as a catalyst, which is they will speed up the rate of a reaction without being used up or consumed in the reaction. Now, this is obviously very important for our biological system, because it means that we don't suddenly need to not only procure substrates, but we need to procure the catalyst as well. It can be recycled. So here is how enzymes work, and this is important. This one. How enzymes work is that if we look here, our reactants still has the same amount of energy. Product, same energy down here, okay? If we compare it with an enzyme, okay? Enzyme, no enzyme. Total energy for no enzyme and enzyme is the same. Total enzyme for our product, enzyme, no enzyme, it's the same. How enzymes work is that they reduce the energy needed to initiate these spontaneous reactions, okay? Imagine that we're trying to roll a ball down the hill, okay? It's downhill, as we can see down here. Sorry, here we go. It is downhill. So what we need here, in essence, this is to overcome this activation energy. This activation energy is kind of like this little hill on the top. If we can find a way to get this ball up this hill, once we get it up here, and then bang, the reaction will proceed, or the ball will roll down the hill and we'll get our product. Now again, this one here is our uncatalyzed pathway. So we can see here, I've got to push the ball up the hill, up, and then boom, it will fall back down. However, if we look at this enzyme catalyzed pathway down here, the hill is so much smaller. It is so much easier for us to push this ball over this hill and have it roll down by itself, as opposed to this one. So this activation energy, okay, is called delta G double dagger. And that's this, okay? Delta G double dagger. And what that tells us is that's the barrier of entry for getting this reaction on and going. Now, here. That is a little bit difficult to sort of put in your mind as to what is happening here. Because if I come back to here, we don't really, our bodies, our chemical reactions here, we're not rolling a ball down the hill. So what is actually happening here? When we have a chemical reaction occur, what we are seeing here, especially with enzymes, is a transition state. And this is important, right? When we have a substrate and we have a product. What is happening here is that, chemistry is that substrate is being converted into a product. Now, if we think about some of those subclasses like oxidoreductase and stuff like that, that is a chemical reaction that is occurring there. So what is happening is that it doesn't just go from substrate to product, bang, straight away, and you blink your eyes and just magic happened. No, there is a transition state. So for instance, if I'm looking at my hand like this, my fist is the substrate. And then an enzyme will catalyze this and turn it into a product, which is open hand. This transition state, you can think of it as like my hand doing this. Is my fist clenched? Is it like this? Is it like a substrate? No. Is it the final product where my hand is completely opened? No. It is an in-between, okay? It's halfway. And what is happening here is our intermediate, okay? And this is what is being denoted by that activation energy. This is the energy that is required to stabilize this the conversion between your substrate and your product. So let's have a look at a bit of an example here. So if we look at this hydrolysis of an ester, okay, we looked at this a little bit earlier when we were looking at proteolytic enzymes, but we have an ester here, and we can, using an enzyme, convert that into an acid and an alcohol. So normally what you would see is pretty much this: ester, and then a big arrow with, say, like the enzyme abbreviations or something like that, or something like that, and then you would have your products. But that's not what's actually happening here. What we're seeing here with this ester, okay, is that in this transition state, and as we can see, this delta G double dagger, that's our activation energy. We are forming this tetrahedral intermediate, okay? So we can see this carbonyl group, this double bond has fallen down here. And we can see this R group here. We've got our OH over here, but an oxygen has temporarily bound here. And of course, carbon is now bound to 4 things, but this is incredibly unstable, okay? It does not like this because of this. So what's going to happen here is that the electrons are going to sort of pull up because it wants to steal these electrons, and the most stable group will be leaving. Now, in this case, what's going to happen is that this OR group is going to leave, and those electrons are going to bounce back through. It's going to form a double bond, and that's going to give us our acid, which is here, and our alcohol, which is this. This is actually going to leave, because something that's actually not denoted in this image is that water is being added here, okay? It's being hydrolyzed. And that gives us our final product of acid and alcohol. Okay, so what on earth does that have to do with this? An ester will break down into an alcohol and an acid by itself, okay? But it will take a very long time. Why is it going to take so long? Because of this. This is really unstable, okay? It does not like this tetrahedral intermediate, and it's incredibly difficult to get it to this stage, okay? It takes a lot of energy. So how does an enzyme help with this? Well, as I've said before, a substrate will bind to the active site of an enzyme. So our enzyme can have various things in here that will hold this tetrahedral intermediate in place and will stabilize it to allow our intermediate here to properly form our product. So by stabilizing this tetrahedral intermediate by the shape of that enzyme, it's going to make it easier to form this product. Does that make sense, everyone? Does that make sense? And that is why with our activation energy here, when we use an enzyme, that activation energy is lower because our enzyme has tools. Its shape, its structure is able to help the reaction proceed past that transition state. Now again, guys, if this is not making sense, please tell me. Please let me know. Okay. So let us push forward. So the catalysis of a reaction takes place in a very specific location of a protein of our enzyme here, which is called the active site. That's what we're looking at here. So the first step when we look at our enzyme catalysis is it's going to be the binding of the substrate to the enzyme. So this one's actually missing a step here. So we have enzyme plus substrate. Okay. Then existing in equilibrium here, it's going to form enzyme plus substrate. So like ES combined. This shouldn't be here yet. Then what's going to happen is that this will form. So let me clarify what I mean by that. So this enzyme plus substrate, what that means is that what we are looking at is enzyme here floating around. Let me go here. So what we're looking at is enzyme is here and our substrates are sort of floating around. Now, if I just put ES, what that is telling me that enzyme and substrate are bound together, but nothing has happened yet. So to clarify, what that means is that we have our ester. Okay, this is our substrate. The ester has bound to the enzyme. So we have the enzyme and we have this ester and it's bound to the enzyme, but nothing has happened yet. It's just made contact. This is our enzyme substrate complex, ES. Then what is going to happen is that the chemical reaction will take place. This enzyme catalysis will take place. This is our enzyme substrate complex. That's what we're seeing here. This is the point that takes the longest with our enzyme catalysis. Then what's going to happen is once the reaction is complete, we will then form our enzyme product. Okay, so this is our enzyme with both our acid and our alcohol present. Then what's going to happen is that product will leave. Okay, it's going to leave the enzyme and be released. This is very important, okay? Because what that is telling us is exactly what is happening in terms of enzyme catalysis. Now, again, looking at this change in free energy versus the reaction. This is still a forward reaction. This is still an exergonic reaction because if we look at the free energy of our substrate, okay, it is when we're converting it from substrate to product, it is releasing energy. Okay, our free energy up here of our substrate versus our free energy for our product, it is releasing energy. But we can see here, this is a gigantic transition state, okay? And that is where the enzyme comes in. It lowers this. And that means that we no longer have to climb up this huge hill and then go right down this huge hill, okay? Because the big thing is, as long as the starting point and the end point is the same, what we are able to do is change how we get there. And that change comes from how the enzyme can best stabilize or, make more efficient this passing through this intermediate stage. And again, I'm going to show you some examples of that in a moment, which will help to clarify things. So this is what I was saying before. Enzymes lower the activation energy. This causes a massive increase to the rate of a reaction because it's able to stabilize and promote the substrate to go to the product by sort of stabilizing it during that unstable intermediate phase. So again, just another recap here. How do enzymes lower this activation energy? What is happening? So enzymes are able to bring the substrates together, to form our enzyme substrate complex. Okay, they're going to bind together. And then what is going to happen is that the enzyme is going to promote the formation of our transition state. This is our in-between, okay? It's not our substrate, it's not our product, but it's somewhere in between. Now, it can do this by a couple of different ways. The first one is it can bind to the transition state through non-covalent interactions, okay? Using these non-covalent interactions, or even covalent interactions as well, to hold it in place and to stabilize it. It can then orient key reactive groups that can interact with these substrates. So for instance, we can have various amino acids form hydrogen bonds or van der Waals forces with our transition state to help stabilize it, hold it in place, and help to promote the formation of that product. Another one here is to provide general acids and bases, to donate hydrogens or steal hydrogens to help ensure that reaction is going to go ahead. Provide an alternate pathway, and as I mentioned here, covalent catalysis, so to covalently bind to that substrate, forcing this transition state and then allowing that conversion of that product. And of course, the last one here is putting torque on the substrate. So just by having the substrate bind to that enzyme, and by having it, bind in a certain way, the enzyme can kind of put can actually twist it and can put bond strain and make it, that certain bond be less stable and make it easier for it to, say, break and bind to something else. So these are ways in which the structure and shape of the enzyme can help in terms of turning our substrate into our product. Okay, so looking at enzymes and looking at binding sites. This is the size of an enzyme here, okay? I actually can't remember what enzyme this is, but that's okay, that's not important. And you can see here, we've got some of these alpha helices, we've got some beta sheet down here. Now the active site, this is the location where our substrate will be binding to. This is where the magic. So, something I just want to point out, again, just linking back to what we did, a couple of weeks ago, is if we look at down here, this is our primary structure. So these shaded amino acids here, that is what forms our active site. So we can see here, this is our active site. This is where this is the substrate that's coming in to bind to this active site here. Look at where they are in terms of primary structure, 35, 52, 62, 63, 101, and 108. They are really spaced out. But because of this 3D folding, because of this orientation in 3D space, look at how close they are in terms of, three-dimensionally. So this is what allows us to form that active site. Okay, the rest of the protein here is working as a scaffold to help support and rotate and orient those key amino acids to ensure that the reaction is occurring as it should be, as intended. Okay, so this is why an amino acid sequence in a protein, it's crucial for a protein to be able to perform its function. The big thing here is that if we have the wrong amino acid in place, if it is in the wrong shape, it won't work properly. So for instance, if the wrong amino acid is placed, so if we accidentally put glutamic acid instead of aspartic acid, what that could mean is because of just how specific a lot of these enzymes are to their substrate, it could mean that the substrate just won't be as effective. That's best case scenario. Worst case scenario, it just won't work at all. Now, looking at our active sites. So again, active site is here. This is where the substrate binds, and this is where the magic happens. So again, here, enzyme and substrate, where it binds. This, where my little pointer here is, that is our active site. So, some common features here. It takes up a small volume, okay? It's not just this gigantic cavern in which billions of substrate can come flooding in, okay? It's very small because it's very specific. These substrates are bound through multiple non-covalent interactions, so the degree of these non-covalent interactions will obviously vary, and it depends very much so on the enzyme itself. The specificity of binding is defined by the 3D structure of that active site and the substrate. I'm going to talk about that more in a moment because that's a very important part. And depending again on the enzyme, water is also excluded, okay? It will only be the substrate and the enzyme itself in that active site, unless, of course, in that reaction, say like the hydrolysis, water is needed. Now, I said here, the specificity is defined by the 3D structure. I want to talk about that because what we have here are two models. We have the lock and key model and we have the induced fit model. Now, the lock and key model is what came first, but then through, further research and further understanding, we then improved the lock and key model to the induced fit model. So let's talk about that. The lock and key model. How I want you to think of this is like you have a house key. What this means is that if the lock to your front door is an enzyme and the key is your substrate, okay? If you take that key and you put it into the lock, it will fit perfectly, okay? That perfect fit of key and lock means that you are then able to turn the key and the lock will move and you'll be able to walk in. Therefore, if you say, have too many brews on a Friday night and you rock up and you sort of open up the door and you hold your hand on the wall and you get your car keys and you slam your car keys into the front door and, it's not working. Yeah, that's what we mean by that lock and key model, okay? You're going to have a bad time. The door's not going to open. You're going to have to sleep outside. That is unfortunate. So that lock and key model means that the substrate and the lock will fit exactly. However, what we then found through further research is that it's more an induced fit model. So like what we saw with cooperative binding, how like when oxygen bound, it caused it to change its conformation so that a second oxygen could bind, etc., etc. That is more so what we see with enzymes. So again, if you rock up to your front door, you put your house key in, what would actually happen is that the little front part of the key would move into the lock and that would cause the lock to change slightly. That will then allow the next part of the key to move in and then the lock would change slightly, which would allow the third part of the key to move in. Then you can turn it. And that's what we can see by this little schematic here. So the lock and key model, substrate, enzyme, they fit exactly and away you go. Whereas with this induced fit model, what we're seeing is that as the substrate begins to bind, the enzyme will sort of change its shape and bind accordingly. And the reason why it does this with this induced fit model is because the enzyme has the highest binding affinity. It binds the tightest to the substrate when it's in its transition state, which is very important. And I'll explain what that means in a moment. We'll do a bit of an example. Okay, so let's look at hexokinase. What hexokinase does is it essentially will smack a phosphate onto glucose, so we'll turn glucose into glucose 6-phosphate. And how I like to think of hexokinase, it kind of looks like a crab claw. Now, when hexokinase, it does not have anything bound here. So this is the active site, just by the way. What's going to happen is glucose will move through into this active site down here. And the binding of the glucose into that active site causes a change to its conformation and causes those arms to sort of move in. And this is what we see when when the glucose to glucose 6-phosphate, when it's in its transition state, okay? The protein itself will actually move in the same way that we saw, say, hemoglobin actually move and change its shape. Okay, so we now, here. So now we have the substrate. We've got the enzyme. The substrate has bound to the enzyme. Let's talk more about how it is that the enzyme is actually lowering this activation energy. So what's happening here is that when our substrate is moving into and binding to our active site, we've got all of these weak interactions that are being formed. And as I've said before, the binding energy is this free energy that's being released, and that the binding energy is going to be its greatest, okay? It's going to have the highest binding affinity when the substrate is in its transition state. Now, how to best explain that is to let's look at stickase, okay? This is obviously a made-up enzyme, and what does stickase do? It is a good enzyme, and its overall purpose is to, well, break the stick, okay? That's what we want it to do. We have a metal stick, and we want to break it. Now, we could just leave the stick for thousands and thousands of years, and you know, the stick will eventually break by itself. But, you know, look, ain't nobody got time for that. So, let us use an enzyme. So, if we're looking at this free energy change here, we are looking at our substrate. The substrate is our metal stick. We then have a whopping great transition state, okay? This is bending the stick. Bending the stick takes a lot of energy. And then we have our product. This is our stick that is broken in two. Now, this is a favorable reaction, okay? It is moving forward. But again, this change in energy from substrate to product has nothing to do with the rate. So, let us now look at an enzyme, but it's complementary to the substrate. Now, as I've mentioned before, okay, the binding energy here is going to be at its greatest when the enzyme interacts with the transition state. So what happens if, again, semi-hypothetically, we have an enzyme that it's not at its highest binding affinity when we're looking at the transition state, but instead at the substrate? So let's say our enzyme here, which is stickase, and it wants to break the metal stick. So what we've done is to facilitate that, the active site here contains a heap of magnets. Lots and lots and lots of magnets to help attract that metal stick and to help bend it and break it. So the way this active site is shaped and all of these magnets in this orientation is highly favorable for our substrate, this stick. Okay, so that's all well and good, but our goal is to break the stick. And what we've kind of done is that in this conformation, it's actually more stable by this. And that's what we can see here, is that we look at our substrate, okay, we can see here there's when the stick has bound to the enzymes, we've got that enzyme substrate complex, and then plomp. It completely plummets in terms of that release of energy. Why? Because look how stable it is. Look at all these magnets that are binding there and holding it in place. That just made our job even harder, because instead of now having to try and find that energy and resources to bend and break the stick, now we need to bend and break the stick whilst trying to bend and move this enzyme at the same time. Okay? This is causing more harm than good. And this is actually a targeted thing that we can do as an inhibitor, okay, to try and inhibit these enzymes, is to find a substrate that can bind to or have a high affinity for an enzyme's transition state, but it can't undergo the enzymatic reaction. So it'll stick there and bind to it, but it won't allow the reaction to proceed forward and will just block the enzyme. So that's why we don't have enzymes that complement our substrate. Obviously, we don't have enzymes that complement the product because we don't have the product. That's the purpose of this enzyme. That's what we're trying to do. What we do see here is enzymes complementary to the transition state. Now, if we were to compare these two, what we can see here is, like, look at the change in our active site in terms of the magnets and where they're placed compared to our enzyme that's complementary to our substrate up here. So we can see this like a big space up here. So what is actually happening is, as our substrate binds to our enzyme, what's then happening is that because of all the magnets located up here, this is favoring the transition state, which is the stick when it's bent. So it's promoting, what it's wanting to do is pull this stick up and form this bent shape. Now, obviously, the stick cannot exist like this for a long period of time. It's unstable. So what's going to happen is it's going to want to hold it and stabilize it in this bent shape for as long as it can until the stick breaks. And then what is happening then is that it no longer, or it doesn't have as high a binding affinity, and it will release that product. Now, if we look at this graph here, this is exactly what we see. We see our substrate. Now, this dotted line is our original curve, which we see up here. And instead of taking a heap of energy to try and break it, because there's nothing here, this activation energy, okay, what we're seeing here is a lot easier to overcome because of the way that this active site is promoting by the use of magnets to bend the stick in this shape. And because this enzyme, because of these magnets, is helping to really bend that stick up, it means it's easier to then break it and release it as a product. So this is how enzymes, this is sort of a good visual example as to how enzymes function to pull the stick down, to bend it in and hold it in that transition state to allow that reaction to finish up and to form out products, in this case, breaking the stick and releasing the product. Does that make sense, everyone? Is that sitting right? Is that sitting well with everyone? Now, again, what I've just put here is just a sort of a written explanation as to what I was just saying to you all earlier. So if we were to compare these three scenarios, okay, C here is by far the most preferable because it's favoring that transition state and it's allowing us to lower that activation energy and thus increase the rate of that chemical reaction. Okay. Oh, good. Yep. Oh, gee. Yes. Thumbs up. Nice. Love it. So let's do a quick recap here of some important concepts that we've spoken about, because again, guys, enzymes is it's a real jam-packed module. Okay, this one's it's pretty full on. So the important concepts that we've covered is that the reaction will proceed only if the free energy difference between our reactants and product is negative. Okay, we do need that hexagonic reaction there. We need it to be a negative, but it doesn't do anything with the rate. How the rate of a reaction is accelerated with enzymes is that it's because enzymes are able to lower the activation energy, because enzymes can provide an alternate path or an alternate method for the way that for the reaction to proceed, i.e. using magnets to help bend our stick to form our broken stick. So enzymes are able to speed up this rate of a reaction. It doesn't do anything to change our equilibrium, okay? Enzymes are not altered, okay? They can be reused. That doesn't mean that they're like infinite, okay? They can, break over time, and they can degrade, so we can then, break them down and create new ones. Enzymes here are stabilizing the transition state. And of course, enzymes differ from other catalysts in that they are specific for the substrate. It doesn't just break any stick or convert any reaction there. It is very, very specific, and it can work in milder conditions like pH 7 and 37 degrees, which quite coincidentally is what we run at. So that is very advantageous for us. So, looking at our alternate pathways. How do enzymes do this? I mean, yes, it will sort of bind that substrate and hold it in place and stabilize it, but it does so much more than that. So, as I mentioned, we've got this covalent catalysis here. So we can form these covalent bonds to this intermediate, stabilizing it, forcing a reaction down a specific pathway. We also have general acids and bases, okay? So I've got, say, particular R groups that are able to be proton donors or proton acceptors, and they can work that way to stabilize tertiary intermediates during the enzyme substrate complex sort of thing. I've got an example of that. I'll show you that in a moment. Same with metal ion catalysis, okay? Very, very useful, being electrophilic and help to shift pKa to help remove things. And of course, catalysis by approximation, by forcing things to smoosh together, it is very effective for ensuring substrate makes product. Yes, okay. Now, looking at some factors that can influence or change enzymatic activity. Enzymes are very sensitive, okay? Enzymes are very powerful at what they do. However, if we change some of the factors, of its environment, it can strongly affect how it's able to do its job. So there are four main factors that influence our enzyme activity. The first one is temperature. The second is pH. These two should come as no surprise for you guys, purely because we understand and know that enzymes are a protein. So temperature and pH are both factors that can denature or destabilize a protein. And because an enzyme is a protein, the change in temperature or a change in pH will also affect our enzymes. Sorry, I just got a weird pop-up thing from my emails. The third thing here is cofactors and coenzymes, which I haven't spoken about yet, but I'm going to talk about that in a moment. And of course, the last one is inhibitors. If we turn off or block our enzymes, it means they're not going to work. Okay, the effect of pH on enzymes. So what pH can do is it can affect the binding of a substrate. It can change the ionization state of an amino acids that are involved. A perfect example of this is how we were looking at histidine 146 with hemoglobin. By changing that pH slightly and by changing whether that histidine molecule was protonated or deprotonated, it affected whether a salt bridge was formed, and it affected the overall shape of that protein. It's the same thing here when we're looking at enzymes. So if we're looking at, say, pepsin here, what we see here with pepsin is that it is found in the stomach, okay? And if we have a look at the, so V0, this is the initial rate of a reaction. With pepsin, it is working at its best. It is working most optimally at a pH of 2. But as we increase that pH, it absolutely plummets. Now, this makes sense because depending on, obviously, the protein in question, pepsin is quite a unique one. In terms of the severe acidity in which it can react in, it works great. But then let's say with our stomach, because that's where we find pepsin, as the chyme moves into our duodenum and mixes with, those pancreatic juices and bile and stuff like that and gets neutralized, what we see then is that chyme will move to a pH of, say, 7.4, like right down here. Which means what will essentially happen is that it'll become denatured, it'll stop working. Which is a good thing because, we're kind of made of proteins and we don't want to break down and digest ourselves. Now, if we compare that to, say, glucose 6-phosphatase. So, again, separate enzyme here. And what we are seeing is that it works very nicely at sort of the high 7s kind of range, which again is very useful because that's what we are. So if we took glucose 6-phosphatase and put it in the same environment as pepsin, it would stop working. Okay, the next one I want to talk about is enzymes and cofactors. Okay, so a cofactor. What this does is it essentially describes a small molecule that is required by an enzyme for it to perform its function. Please don't fall into this trap, okay, of thinking that a coenzyme is like two enzymes that work together, okay? That is not what happens here. What it is how I want you to picture this with our coenzymes and cofactors is your car keys. Okay, your car is an enzyme. It is a fantastic tool to accelerate the reaction of you going from point A to point B. Beautiful. However, your enzyme, i.e. your car, will not work well unless you turn it on. You need a certain thing to activate and turn on your car keys. So in this sort of analogy, you could think of a cofactor as your car keys, okay? Your enzyme, your car, will not work without the car keys to turn it on and activate it. And that's what we see here. So with our cofactors, okay, it can be one of two main sort of subcategories, a metal ion or a coenzyme. So we have our cofactor and a coenzyme. I want you to only know the difference between a cofactor and a coenzyme. So both perform the same function, but cofactors can be either metal or organic molecules, whereas a coenzyme is just, it's only organic molecules. Does that make sense so far, everyone? Okay, so let's go up. Let's just do this for a moment. So let us have a look here, just as an example of a metal ion catalysis. So actually, no, this is a better one. Sorry. I'll come back to that previous slide in a moment. What we see here is carbonic anhydrase. We were talking about this last week when we were talking about hemoglobin and myoglobin. So when we have carbon dioxide would be converted with, so carbon dioxide and water would be converted into carbonic anhydrase and then would be transported by the red blood cells to the lungs. So this is how it actually works. So carbonic anhydrase, it uses zinc as a cofactor and allows us to allows each one enzyme to hydrate 10 to the 6 molecules of CO2 into carbonic acid per second, which is kind of ridiculous. So let us go through now. Let's have a chat about how this works. So we have our zinc molecules. So zinc is bound to 3 histidine molecules, and what it's doing is it's working to want to draw electrons away from our water molecule and essentially make it more acidic. So we're wanting to get this OH and pull it towards this zinc. Now what this is going to then do is with that water, it's going to be a powerful nucleophile, which is going to be attracting this CO2, okay? This is very much so due to the effect of this zinc. Now, as this happens, as this oxygen binds to this carbon, obviously what we've done here is we've broken this double bond, okay? This double bond over here, and this is not stable, okay? This is our transition state. So then what is going to happen is that water is then being converted to bicarbonate, and the process is complete. So what is happening here is that zinc is able to not only kickstart this process, but will also stabilize it during this period of instability. Another example that we have here is looking at enolase. So enolase is looking at being able to convert 2-phosphoglycerate into PEP, which is phosphoenol pyruvate. This is a step, I want to say step 8, but don't quote me on that. I could be wrong. With glycolysis. And what it does is that glycolysis is where we convert glucose into pyruvate. It's the first of 3 main steps in the production of ATP. So what's going to happen here is that we have our 2-phosphoglycerate, okay, that's this molecule here, in here, and it's going to bind into enolase. So just to be clear, we can see that this sort of shaded part here, this is our enzyme enolase, and we are zoomed right in on the active site. Now, what's going to happen is that this 2-phosphoglycerate is going to move in here and bind to enolase. And one of the key amino acids here in this active site here, lysine 345, is going to function as a base catalyst by trying to steal this hydrogen here from this 2-phosphoglycerate. What that will then do is cause the electrons to jump up and cause these electrons to jump over here. And essentially push those electrons up towards this carbonyl carbon group. Now, again, incredibly unstable, but because of these positive magnesium groups up here, they are being attracted to the negative oxygens and stabilizing them and holding them in place. Now, again, sorry, I've just caught up a bit here. So this is what I was saying here. This enolate that's being formed, it's very unstable. However, because of these 2 magnesium ions, it's holding it and stabilizing it and ensuring that the reaction can take place properly. So what we're seeing here now is glutamic acid, and that is going to then function as an acid catalyst. Okay, and it's going to allow this hydrolyzing of the hydroxyl group on the side here, and it's going to form water as a final product. So what that is going to do is it's going to cleave that off. It's going to then cause all of these electrons to shift and jump around. It's going to release water as a byproduct and then release phosphoenol pyruvate, and the reaction is complete. But we haven't reset yet. So what's going to happen is that the glutamate here is going to steal a hydrogen from this lysine 345 and reset us back to the very beginning. Now, would I expect you guys to memorize this pathway like that? Absolutely not. What I would expect though is if I was to say, give you this diagram, could you explain to me, using your own words, what is happening in this reaction? That is what I would expect from you. Okay, how are we feeling, guys? How are we going with everything? Do we need a quick breather? Do we need a quick 5-10 minute break? Or are we good to soldier on? Actually, I just double checked. We've only got a handful of slides left. We will soldier on. Then we'll have a bit of a break before our shoot workshop. Let me go here. Here we go. Now, let us look at another enzyme, chymotrypsin. Chymotrypsin is really good because it uses a whole lot of different enzyme mechanisms that we've spoken about, that we've discussed today in terms of how it achieves that proteolytic cleavage. So, with chymotrypsin here, it has an active site. Okay, it has a catalytic triad, and what that means is that there are 3 very key, important amino acids that are found in that active site. Now, scientists were able to determine and find out that serine 195 is one of those 3 key amino acids because what they did was they reacted it with DIPF. Okay, so that's the diisopropyl phosphofluoridate. And what it did was it essentially irreversibly bound to serine and caused it to stop functioning. And when the scientists did that, when they took DIPF and reacted it to serine 195, the enzyme completely broke. So that was important because what that essentially told scientists was, okay, if we break this one specific serine, the entire enzyme stops working. So therefore, this is a very critical spot for chymotrypsin's overall function. And of course, they were 100% correct. So with chymotrypsin, let's go over here. What we have is a catalytic triad. Now, our catalytic triad is serine 195, histidine 57, and aspartate 102. So what we have here is serine 195, and what it does is it carries out a nucleophilic attack on our peptide. But there's a problem. It's not able to do that just by itself. We need something that'll make serine more reactive. This is where histidine 57 comes in. So histidine 57 is like, in the terms of a three-dimensional shape, directly next to serine 195. And what is happening here is that it's functioning as a base catalyst and sort of putting strain on that serine 195 because it's sort of trying to grab and steal this hydrogen. So by putting that strain on there, by sort of attracting it and pulling it, it's making this oxygen far more reactive. Now, histidine is able to do that because of aspartate 102, essentially acting as an acid catalyst and is functioning here to sort of put strain on that histidine 57. So what's essentially happening here is that we've got that catalytic triad and they're all putting strain on each other and making it nice and taut, like a trampoline almost, and sort of locking and holding everything there. Now, I've got a YouTube video that I will show you guys in the Tute workshop just because it is super, it's just a lot easier, essentially, to show you guys. So we'll go through that again in the Tute, and we'll spend a little bit more time going through chymotrypsin as well. But with chymotrypsin, as I said, it will cleave after an aromatic amino acid. So let's go through it. Let's have a look at this mechanism here. I'm still in the way. There we go. So what's going to happen is with chymotrypsin, it is going to cleave a peptide after an aromatic R group. So if we look at this substrate, okay, we can see we've got, the peptide before. We then have our aromatic R group. The cleavage will occur here, directly after that aromatic R group. And then we have the rest of our protein over here. Now, what is being done here in this overall schematic is it's just being simplified here. So what's going to happen is that this peptide is going to then move into this active site and it's going to push on this catalytic triad, okay? It's going to actually like physically push on it because it's making contact with the enzyme and this active site. So what will then happen is, and we can see this is our peptide group here, by physically pushing on this catalytic triad, what that is going to do is swipe this hydrogen and it will make this oxygen be nucleophilic, and it's going to want to bind to and attract to this carbon that is involved in that peptide bond. Now, this part seems a little bit tricky. So what is then going to happen? Let me do this. Here we go. So what is then going to happen is that when we have our oxygen from our serine bind to this carbon, this double bond will break. Now, something to keep in mind here, and I'm not sure how in-depth this was covered in your other classes, and that is a sigma bond is longer than a pi bond. What that means is that if we break one of those double bonds, okay, because remember, a single bond is a sigma bond, and a double bond is a sigma and a pi bond. So if we break that double bond, we're breaking the pi bond, which means that the distance between our carbon and our oxygen here is getting longer. Now, and again, if we look at this single bound oxygen here is very unstable. But we are able to stabilize and hold on to it temporarily due to this oxyanion hole. What is happening here is that the hydrogens from our serine 195 and glycine 193 is these hydrogens here are then sort of being attracted to this oxygen, and it's stabilizing and holding it in place. What that then allows us to do is then stabilize our tetrahedral intermediate. The electrons from this will eventually fold back down, reforming our double bond, and the the most stable thing is that the hydrogen will then be stolen from the nitrogen with our histidine. And what's going to happen is this bond between the carbon and the nitrogen, which is where our peptide group was, will actually break. This means that there's nothing here holding the left side of our protein in place, and it will then leave. That's one of our byproducts. Now, we can see here our amine product has left. Okay, cool. Here. So the amine product has left, but we kind of have a problem here. And that is that we still have the first chunk of our protein still attached to our serine 195. So this amine has pinched a hydrogen from this nitrogen here from our histidine 57 and has now left. So we've done half the job. How do we get rid of the other half of our protein? Because we can't just leave it here. We still need to remove the rest of that protein as a product. Now, what has happened then is that because the leaving of this amine group, that then allows a water molecule to come into place. And in the same way as the that we saw the attack happening with the peptide, or not the same way, but slightly similar, and that is with our histidine 57, it's going to want to attract and grab on to the hydrogen from water, which in the same way it caused strain with serine 195, it's going to cause strain on this water molecule, and it's going to force the oxygen for our water molecule to attack this carbonyl carbon of the other half of our peptide. Now, what that is then going to do, so this is what I was explaining here. It's going to cause this hydroxide to be more nucleophilic. It's going to want to attack this carbon, and it's going to form another tetrahedral intermediate. And that's what we're seeing here. We can see this histidine 57 grabbing onto and putting strain on our water molecule, which means this oxygen is going to want to nucleophilically attack this carbon here. We're going to form a tetrahedral intermediate. Remembering that a sigma bond is longer than a sigma and pi bond, so it's going to extend outwards, and it's going to form these hydrogen bonds with serine 195 and glycine 193. Then what is going to happen is that the electrons are going to fold back down, but instead of cleaving here, what is going to happen is that the bond between the carbon and the oxygen of serine 195 are going to break. What this means then is that the other half of our protein is then able to leave that active site, and the same attraction between our serine 195 and that histidine 57 is going to occur again, and that will then allow the re-establishment of that sort of the bond strain between serine 195 and histidine 57, allowing serine to act as a more nucleophilic and allow it to react and work again to cleave more proteins. Ooh, holy dooly. Oh, whoopsies. Let me go here. And that's what we can see here in terms of the release of our final product. And we can see that the catalytic triad is back to how it was at the very beginning. All right. My goodness. Let me go back to here. So guys, that was a lot to take in, okay? That was a lot of information. So what the game plan is now, look, take 5-10 minutes, okay? Go for a quick walk around, grab a drink, okay? Go do what you need to do. And what we'll do is we'll start up that Zoom session, and we will start the Tute workshop where we'll talk about your upcoming assignment. We'll talk about the first assignment, and we'll break this down even more. Wow, too much. Yeah, I know, guys. It's a lot. It is a lot to take in, okay? These next 2 weeks are going to be big weeks. So what we'll do is we'll go through chymotrypsin a lot more, and I'll do my best to sort of help you guys out and answer any questions that you may have. All right, guys. So again, the instructions on how to join the Zoom are in the Moodle page. What time do we start the shoot? Let's say 3:50, 3:55. So around 10, 15 minutes, we'll kick off there. And it's blah blah blah. Words are hard. Words are really hard, guys. And what we'll do is we'll go through some questions, and I'll help you guys out in terms of digesting this material a little bit easier. Oh no, the sad and injured emojis. Oh no. That's all right, guys. Look, we'll get you guys all fit and repaired and healed in our shoot workshop. Alrighty. So thank you very much for joining me, guys. I will see you in like 10 or so minutes in our Zoom class. All right, see you soon.